Yeah. So thanks to organizer for giving me opportunity to say something about the hydrogen, because hydrogen is a future fuel now, and we feel that within a 6-7 years we'll have hydrogen um, fuel as a cheap source for the automobile sector, as well as a fuel in for other applications. Hydrogen is a very rich energy resource, and it is lightweight. A small amount of hydrogen gives huge amount of energy. That is the big thing in the hydrogen, and it is a green fuel. So worldwide, people are talking about hydrogen and their application in the automobiles. Like people are talking about hydrogen engine now, so you can use directly hydrogen as a fuel in the automobile. And the current user is the fuel cell technologist, because hydrogen is an input for the fuel cell, and fuel cell is a mature technology. SOFC, solid oxide fuel cell, is a almost minimum 40% efficiency of people are talking, and that is good enough for even buses and heavy vehicles. So I thought that we should have this discussion on this hydrogen, and we are also working on the hydrogen with in collaboration with other industries as well as some academic institutions. So let me introduce about my organization first. The Center for Materials for Electronics Technology is under Ministry of Electronics and Information Technology, and this is a labs. Those are working on the electronic materials for electronics, and we also work for strategic sectors like DRDO, ISRO, and BRNS, and BRC, and other people, atomic energy, because their requirement is very small. So we just give the materials to them, whatever materials required to them for their purpose. So Pune lab, we are working on high purity materials for electronics. Maybe we are pioneer in polymers, pioneer in glasses, composites, nanostructures, all kind of nanostructures we make in the Pune lab. And a variety of applications we are talking today now: fuel cell, solar cells, thermoelectrics, and all these kind of things. Our Thrissur laboratory is working on ceramics, electroceramics, like VJT, NTC thermistors, ferrites. All kind of things are required in the electronics. Our Hyderabad laboratory is working on pure metals, because pure metals are required in the electronics, like pure semiconductors, silicon, tellurium, cadmium, mercury, all these kind of 99.999 5N purity, 7N purity, we are working on that. So to establish because the electronic materials requirement in the market is very less today, but that's why the current trend was to import electronic materials from the other countries. But now there is a need to the country that we should have our own electronic materials for the electronics. This is a CIMET Pune activity. The very important activity, while like LTCC packaging, low temperature co-fire ceramic packaging. This is electronic packaging. So any device you want to make, then we want to connect the circuits each other, and multi-layers you have to connect and pack it. That electronic packaging is very important, and this electronic packaging We have a good facility for this electronic packaging, almost 1,000 square feet, 2,000 square feet. We have a clean room, and inside we have all kind of equipment, packaging equipments. Now we started working on material also, so materials with packaging. So this is one of the good facility we have, and I think, of course, all our students and all faculty members can use this facility because it's a unique facility and will not be available in other places. So people can, students can come here for 2-3 months and make their devices. If there are innovative ideas, they can share innovative ideas and make a different kind of devices, because this is the need of the country today, because you know, in this very panic situation, we are handicapping some of the devices, some of the materials, because we are not producing it. We have to take it from outside. Now this time has come to, we should have our own materials as well as devices. So this is very important. We have a facility, but we need to go ahead with some skill development and make such kind of devices with trial errors, with simulation, everything we have to do, because this is needed for the country now. Then non-metal alloys, all kind of nanostructures we do, like metal alloys, nanoparticles, then semiconductor oxide nanoparticles, their respective chalcogenides, also we can work. The uniqueness our nanostructures are, we grow nanostructures in glasses, we grow nanostructures in the polymers. It's very important to applications of this polymer, nanocomposite and glass chemistry observed, because controlling particles in the nanoscale up to 1 to 2 nanometer is possible in glass and possible in polymers, and this quantum dots of such kind of things in these matrices definitely gives a variety of applications, and I will just give some glimpses of the these nanostructures, how they are helpful in many applications. The main area we are working now, hydrogen generation, and the source we are using water and plenty of H2S available. Now we started with methane gas also. We started working on it because hydrogen is a very important, and today hydrogen problem is not a the process today we have is a very expensive process, and hydrogen we produce is a highly very costly hydrogen. See, anybody producing any fuel, so it will be compared with the fossil fuel like petrol and diesel. Okay, so unless and until we compare our cost and your efficiency with the present fuel, it cannot be economical. It means we cannot be used, or we cannot be explored for the other applications. So here the point is how we can make very cheaper hydrogen. That is the requirement today. If you will able to make cheaper hydrogen, then definitely we can explore the all application of hydrogen in any in automobiles or anywhere wherever we need it as a fuel. Then we have a good solar cell facility, solar cell fabrication facility. This is a very useful facility for the students and for the faculties. They can come, they can collaborate with our scientists and do something. Like silicon solar cells, people are talking today. It's a very mature technology. Guaranteed efficiencies around 14%, 13-14%. People are talking on 18%. We want to really go to beyond 14% in silicon solar cells. We get cheaper material. The problem of silicon solar cells is it occupy a huge space to the panels. We need to think about other materials which can useful for the solar cell applications, and people are talking to today now this quantum dot solar cells. So quantum dot silicon solar cells, quantum dots of silicons. People are talking about 61% theoretical efficiency. It's very difficult to get 61%, but we could achieve 25%, 30%. The device can be managed. That means your panel size will reduce, and cost-wise also it will be come down because of you need a very smaller area. Then other area is a perovskite solar cell people are talking about. Though perovskite solar cells has a lot of problems of stability. So perovskite solar cell people talk 22%, 24% efficiency, but the stability of the material is a problem. So we need to somebody needs to work on it because it's a continuous process. Because solar cell is activity is not going to die in the country because we have plenty of solar cells, plenty of solar light available almost 8 to 9 months. So we need to work on that, and we should utilize that kind of the reservoir which we have. Then dye-sensitive solar cells, that is one of the things. Then fuel cells. Fuel cells, we work on solid oxide fuel cell, but not conventional. We started working on LTCC based fuel cells because LTCC, low temperature coated ceramics based packaging, we want to introduce in the fuel cells. Though it is a costly, but it's a very sturdy, and how we can reduce the cost. Then we have PM fuel cells, polymer membrane, PM fuel cells. Where we are working on we are concentrating on the catalyst like platinum, nickel, cobalt, carbon combination. Everything is available with us, graphite plate, everything is available. So only the efficiency of the PM fuel cell depends on the catalyst, and that enhancement is we would like to work on that. So we developed some platinum. We replaced platinum with nickel. We replaced with cobalt combination, and it's a nanostructure. It's 5 to 10 nanometers of nickel and cobalt, which definitely enhance the efficiency of the PM fuel cells. Another area we have started is thermoelectric cells. That we'll talk later on. Then energy storage materials. Energy storage is a very important area because what may be energy would like to we produce the energy, but how to store the energy and use it whenever you want. So very highly efficient energy storage device is very important today. And today the battery, lithium-ion battery, is one of the battery chemistry with lithium-ion is giving much more energy density as compared to other batteries. Considering lithium, the lithium availability, people are talking today whether we can use sodium-ion battery because plenty of sodium is available, sodium chloride is available. So whether we can use that. So both the chemistries we are today, but we are focusing more on sodium because in the country we have a lot of sodium. So we should have the sodium-ion battery comparable to lithium-ion battery. So that is the theme of this project, and we are working on that. We have a good project. Many students are working on this. See, in 4-5 years, all devices will be flexible devices. Okay, your TVs will be flexible. Your computers, your laptops will be flexible. mobiles will be flexible. So we need a flexible battery for it. We cannot use a conventional battery for this, because whenever we want to go to, when the flexible TVs we can carry with you in the while traveling, and whenever you want you can watch the TV. So, and for this flexible batteries are very important. So flexible devices require the flexible batteries, paper batteries. So we started working on that. Everything changes when the shape changes, everything changes. The material, their material quality, material specification changes. So materials are very important. All these are material driven applications. Okay, like battery, solar cell, hydrogen, then everything is. So materials are very important today, because all technologies are materials based technology. Then metal air batteries are introduced because metal air batteries have more energy density as compared to other batteries. So we started on aluminum air batteries, magnesium air batteries, where we find, though the voltage of these batteries is less, 1.5 to 1.7, not like lithium-ion battery voltage, we can go up to 3.7 to 4.5 electron volt. Some of the materials, the voltage dependence again in the material characteristics or electrolyte characteristics. Like now ionic liquid have come in the market, we can go up to 5 to 6 volts using ionic electrolyte in the lithium-ion battery. So these kind of combinations we are trying. The major group is sensors. We are working on gas sensors, all kind of gas sensors. But now we are focusing more on optical sensors, because in automation, optical sensors are much more effective as compared to conventional sensors. LTCC based pressure sensors, magnetic sensors, now we introduced, very steady one. And for agriculture, we are trying NPK sensor. That is also optical sensor, because farmer cannot wait for, because whenever he submit the samples, then they will try ICP-MS, ICP-US, and then see phosphorus, nitrogen. It takes long time. Whether we can have the device put on soil or the leaf of the plant, where we can check nitrogen, phosphorus, sulfur immediately within 1 minute or 2 minutes, 3 minutes, so that farmer will come to know what is the deficiency in the soil, what is the deficiency in the plant. So accordingly doses can be. So this is very important for the country, for the advancement, for the yield, for increase the yield of the crops. Then thermoelectric materials. Thermoelectric materials, two types of thermoelectric, Seebeck effect and one is a Peltier effect. So in thermoelectric materials, if a Seebeck effect means energy generation, if you have applied the voltage, when we apply the voltage, that when there is a difference in the temperature of the material, okay, that heat, the absorption of heat give the energy generation. In some of the materials has that properties. Other way, when we apply the voltage, you will get cooling effect other end in the same thermoelectric materials, like is the Peltier effect. So these materials, development of these materials, and how when you nanostructure these materials, whether we get some benefit out of it, or we can enhance the energy generation, or we can get more voltage, or in small voltage we can get good cooling effect. Smaller coolers in the for the farmers, because it doesn't require much maintenance. So we can combine with the solar light, use the heat the generated by the solar light and make some combinations. So we are thinking how to do that, because this is very important, because the today's cooling devices have the very huge, they require a huge amount of electricity. But such kind of coolers, if they can work on the solar cell or solar light, definitely these coolers can be useful in the rural area, in the and useful to the farmers. They can store the grains. You can store the milk at 10 degree, because today you see milk problem today is we do not have sufficient cooling arrangements for this milk. So transportation is problem. All these things are very has to be taken care when we are developing some of the good things. Then radiation shielding materials. Radiation shielding materials means we develop X-ray absorbing material, then we develop IR absorbing material, UV absorbing material, because these are required in some of the devices. Some of the like X-ray shielding material. X-ray shielding material is the lead. Lead has to be replaced. So we replace the lead with something else, nanomaterial, and it gives the same X-ray absorption. So this kind of activities we have, and we lot many things we do in our laboratory, and we need good engineering students or faculties who can also use such kind of facilities. See, any materials you want to develop, so their properties needs to be checked, because unless and until we come to know the properties of the material, we cannot predict where it will go, or what is their application. So all these material, all these equipments are needed for these material characterization, like X-ray diffraction, scanning electron microscope, three-dimension scanning electron microscope, three-dimension transmission electron microscope, APAM, SPM for the thin films, for the basically required for the solar cell, UV, IR, PL spectroscopy for photonic application, thermal analysis. We want to make, if you make the material, whether how is the thermal property, how it behaves thermally. Then surface area, particle size analyzer, 3D X-ray. We can scan the material and see what is the porosity in this. X-ray detection, electrochemical workstation. We can check the electrochemistry, electrochemical behavior of the materials. Is a part. Impedance is also part of that. Thickness measurement and potentiostatic. All these are required for when we are doing such kind of in the energy. This is one of the technology we transferred. It's a light sensor, street light sensor. It is a photoimmeasurable paste type material we developed, and we transferred to ceramics. And this is the lead-free X-ray absorbing material we developed. We made aprons out of it. The red apron is a lead apron. Is a 5. The weight of that apron is 7 kg. We can see in our picture one of the student wear this blue one. It is a 3 kg. So that is the difference of the nanostructure. Now we announced the technology for transfer. As the LTCC, I would like to give some idea about the LTCC materials. What is our plans and all this, so that we need the students can understand what we are doing it. So magnetic field sensors for international thermonuclear reactor we developed. We see very complicated structure. We can circuits we can make in LTCC. Same like a pressure sensor for aircraft engine we developed. You can see this is a pressure sensor. Now future plan of this test sensor for fusion reactor and participant real-time river pollution monitoring. All these sensors can be integrated in LTCC, and which can be used for river monitoring. water monitoring, and this is again I told you that solid oxide fuel cell. So it can be the packaging can be done LTCC. So that is one of the good project we have. This is a solar cell facility. We have all kind of. We can make thin film solar cells. We can make perovskite solar cells. We have all facility here, fabrication facility. So people can, the student can use this facility and for their project. This is our battery facility. We can make all kind of batteries, lithium-ion battery, sodium-ion battery, we can aluminum-air battery, all kind of batteries, rechargeable batteries we can make. We have a center of excellence in rechargeable batteries. If any student have the ideas, some kite flying ideas, and say that I have I can fabricate a battery which can give much more energy density. They can come in this. They can join this center of excellence and work for 2, 3 months, 4 months, and prove their ideas. So recently we have started it, and we would like to explore for the students and industry so that they can come and join and do their chemistries and design, BMS, everything they can. This is our mobile. The final target is the e-vehicle, and will support the industries which are going to manufacture lithium-ion battery, because we have the main backbone of the battery is the single cell, which people are importing. Now we have this, so we can transfer it and do that. Simultaneously, we have flexible batteries devices. We have come to this very small scale flexible cells. Now we would like to make a tape-like cells so that we can wind it and use it for many applications. All kind of nanostructures we make, like you can see semiconductors, nanometals. When you nanostructures it for very few nanometers, definitely gives very fantastic applications. Like quantum dots embedded in glass, metal nanoparticle in glass is our specialty. Nobody knows. Nobody is. If we go to the literature, you can find that quantum dots embedded glass is only we do, and the specialization of metal nanoparticle in glass is also we took some 15 years to establish, but now we are pioneering this, and now we are exploring many applications of this. Polymer nanocomposites, all kind of nanocomposite we can make for conducting and optical applications. See the structures of nanostructures we do. This is the graphene, then this is a very highly porous structures, honeycomb structures, then a flower-like structure is a porous structure again. Each petal is very thin, few nanometer scale, 1 nanometer, 2 nanometer scale. Okay, but the porosity is so high, the aspect ratio is very high. Like hairy kind of structure is required in sensors, we do it. And how the 3 categories zinc oxide shows 3 shapes: rods, cups, and needles. All are because of the processing, how we can synthesize. And this is quantum dot copper sulfide. We can see various uniform structure or uniform quantum dots of few nanometers we can make. Very important for the applications. These are the graphene. We can make now graphene in our lab for different purpose. For solar cell, for batteries, for thermoelectric applications, supercapacitors applications. They are very good energy storage material, supercapacitor and battery. There are 2 devices. One is a battery and one is a super. Battery has a high energy density, supercapacitor has a low energy density. Battery has a high power density, battery has a low power density, supercapacitor has a high power density. So it's So we are trying combination of both because we need high power, we need a higher energy mix. How we can combine together and see. Some of the application we wanted very perforated graphene. So purposely we perforated the graphene and used for battery applications. How to make nanostructured materials in your large scale. This is a plasma reactor. In this plasma reactor, we can use, suppose you want to make metal nanoparticles like aluminum. Then aluminum, aluminum will be one of the cathode, it get vaporized. Aluminum vapor get condensed at molecular level, and we get nanoparticles of aluminum. Nanoparticles of aluminum is very difficult to make by other route, but this is a very, so we can make aluminum, we can make copper, we can make titanium, all kind of things we can make it, and the capacity is 200 grams per hour, 300 grams per hour, something like that. So we supply to DRDO and other people for the very aluminum particle required in the as a propellant, as oxidizer. This is aluminum nanopowder we make. Though you see the very bigger one, but they are smaller particles accumulated and give the very ball kind of structure, but they are very fragile, and we can use it for propellant applications. Copper nanoparticles, very high purity, very smaller size of 10 to 20 nanometer also we can make out of it. A good indication of formation of copper nanoparticle is when copper nanoparticle comes out. When copper nanoparticle comes out, and when as soon as you get exposed to air, then temperature goes up to 800, 900 degrees centigrade of that material. Means it is exothermic. Oxidation is exothermic, and it will become red hot. So this is a good indication of that, and we observe many times in the laboratory. One day, our first and second run of copper nanoparticle, somebody has opened the bag. As soon as that bag opened, and it fell down on the carpet, and carpet started burning. So because of these nanoparticles, so it was showing that it's a good the nanoparticles are formed, copper nanoparticles are formed. Now we'll go to the hydrogen. Very important topic today, because why hydrogen is important. I told you that it's energy rich fuel. Small amount of hydrogen has plenty of, means the calorific value is very high, and it is a green fuel. Everybody knows that how it is green fuel, and it's a lightweight. So people are thinking that hydrogen will have the future, because very high is energy rich, and if you produce hydrogen at a cheaper rate, definitely hydrogen will have a scope in future as a important fuel. All applications we are talking, like automobiles, fuel cells, cooking, and electricity, all these applications can be covered by the hydrogen, where heavy vehicles can be run on hydrogen, because it's very, see, you can see 258 kg of hydrogen, almost 260 kg of hydrogen. The car can go up to 30,000 kilometers. You can see the cost calculations, how this energy richness of the hydrogen. So you can see that how this hydrogen can be. I will show you first how this hydrogen is useful in the fuel cell. people are talking so many, how to make this cheaper hydrogen. So cheaper hydrogen can be made through use the combination of photovoltaics and the combination of photovoltaic cells and electrolytic process together. Then is a photocatalysis process. Use the sunlight for the catalysis, use semiconductors for it, and produce hydrogen. And same can be useful for these fuel cells. The fuel cells can be used for your laptop, not for laptop, but desktop computers, your UPS systems. So the cheaper hydrogen definitely will have the useful in the consumer electronics as well. This is a fuel cell car already in the market. You can see that hydrogen can be filled. Hydrogen charge station we have here very soon. So everybody knows this hydrogen, how this hydrogen used as an input for the fuel cell, and you can see that the byproduct is water in this. So it is again it's a green process. So considering the importance of hydrogen, today's problem is the cost of the hydrogen. Cost of the hydrogen is very high. So we need to have very cheaper process for the hydrogen production. The current process is a steam reforming process. Methane steam reforming. So methane can be used, reacted with steam, and we get hydrogen and carbon dioxide. Electrolytic process. Electrolytic splitting of water. Huge amount of, again here, huge amount of energy is required, electricity is required to produce hydrogen. Biochemical process. We can produce hydrogen. Again, it's a very slow process, and yield is low. So this is the process. You can see the present process, steam reforming process. Methane is oxidized through water, and we get hydrogen and carbon dioxide. So final product is carbon dioxide and hydrogen, but it is again a separation problem. Okay, so that's why it makes the process becomes very expensive, and hydrogen production is very costly. We have plenty of H2S in oil refineries, whether we can utilize that for this hydrogen. Currently, we are making through class process, it's a liquid sulfur for our agriculture. It is the one of the good processes that we can see today is a photocatalysis process. Photocatalysis process is a very it's not like normal catalysis process. The catalyst is a semiconductor catalyst. Semiconductor has the property that when it absorbs the light, maybe some of the materials are like the band gaps in the UV region, means wide band gap material, they absorb UV light, maximum UV light, and there is a photo excitation. Electrons and holes are generated. When we can make free electrons through this process, these free electrons are responsible for the reduction of water into hydrogen and oxygen, or H2S, hydrogen and sulfur. What we have to do here, anyway, see the photocatalyst by UV light and photocatalysis in visible light. Visible light means your band gap should be in the visible region, almost 2.4 electron. Means your material should absorb the sun, the light from 400 nanometers to almost 600 nanometers. That is a visible region. So we need to tune the band gap of the material from 2.1 electron, 2.8 electron volt to 2.0 electron volt, so that we get more electrons and holes through this process. What we do during the process, suppose like we have a TiO2 titanium oxide is a good UV light catalyst. If you can use UV light for this TiO2 zinc oxide where their wide band gap is there, they absorb UV light and generate maximum electrons and hole pairs. I want free electrons. What I will do, I will trap the holes. Trap the holes. So free electrons are available, and these free electrons are responsible for the splitting, water splitting. That huge amount of energy is there in electrons, because any electrons and holes are generated. Electrons and holes always have tendency to recombination. They have a recombination process. We stop that recombination process. So electron becomes very unstable. He wants somewhere to give his energy and stabilize it. So use that energy for this purpose. So we have water source, very cheaper source, no temperature, room temperature. At room temperature, when sunlight falls on the semiconductors, they produce electrons and holes. And during this process, trap the holes. So free electrons are available for the hydrogen production. So what we do, suppose you want to use the sunlight as a source, then tuning of band gap is very important. Tuning of band gap is very important. So we synthesize sulfide semiconductor, oxide semiconductor, or dope with something like TiO2 doped with nitrogen. We can tune the TiO2 band gap in the visible region. So that we do it. See the thermodynamics of water splitting. Delta G0 237.19 kilojoules per huge amount of energy is required to split water into hydrogen also, but still it is possible through this process. S2 is only 33.44, very small amount of energy is required for the splitting. So this is the process. At room temperature, we can have a catalyst here. We can in the water. We can expose to sunlight. The sunlight falls on the particles, and this photoexcitation takes place. These semiconductors and electron holes are generated. And during this process, holes are trapped. Some of the sacrificing agent be used, and this hydrogen generation efficiency can be increased. So this is the catalyst we use, like nitrogen doped NB2O5. NB2O5 in UV region, when you dope with nitrogen, it becomes in visible region. Means their band gap is around 2.4 electron volts. Initially it is 3.2 electron volts. And see, we produce nitrogen here. This is structure. When you dope with nitrogen, the NB2O5 becomes little porous, and because of this porosity, as well as nitrogen doping, the maximum sunlight absorption is taking place, and electron holes are maximum electron holes are generated. So here at the different of nitrogen percentage I have given, at optimum nitrogen doping, we get a good hydrogen production. This honeycomb-like structure, MOH2. See the structure of MOH2, we can synthesize. This is a very, see the whites like honeycomb. Because of this pore structure, we get good photocatalytic activity, hydrogen production. Very straight, you see, there is a linear hydrogen production we observe. Then we combination of cadmium and molybdenum together. Structures are like flower-like structures, and you see porosity is increased. Also gave good photocatalytic activity. Tin oxide, people have used SNO2 as a material, but we've observed that SN304 is one of the oxide of SNO2. Has the band gap in the little visible region as compared to SNO2, and we can you see the hydrogen production here, SN304, very linear hydrogen production we observe it. Then combination of TiO2 and cadmium, like UV material and cadmium medium sulfide is a visible light material. When two compounds come together, they form the heterojunctions. They form the heterojunction in the between two particles. During that, what happens when the photoexcitation takes place? Some of the electron these heterojunctions are helpful for transferring the electrons to the surface and trapping the holes during that period, and that enhances the photocatalytic activity. So we did this paper in last year, and we found that this TiO2 cadmium medium sulfide gives good photocatalytic activity, good hydrogen production. Then zinc tungstate is again a good photocatalyst for in the UV region, but we sensitize with cadmium sulfide with a very cadmium sulfide is in the visible region. So cadmium sulfide sensitized with solar light, and it gives electrons to the zinc tungstate, which enhance the photocatalytic activity, which gives the hydrogen production. This green line, you can show good hydrogen production. So all these kind of structures we develop for. I will not show all kind of materials, but all these glimpses of the material like zinc indium sulfide in two forms. Like one is like this structure. We have a lanthanum indium sulfide wires. Then his very highly crystalline lanthanum indium sulfide structures. Then we dope zinc oxide with silver and found at good photocatalytic activity. Then cadmium indium sulfide, we have flower-like structure as well as nanotubes. And nanotubes gives better catalytic activity because of good crystallinity and all these things. So, and this is the. We also have this is I will show you that one of the big reactor which we have in our premises. Then I told you we have a capability to produce nanoparticles in the glasses. So these cadmium sulfide quantum dots, cadmium selenide quantum dots, cadmium selenide, bismuth selenide, bismuth, all these are grown in the silicated glasses. And you can see band gap. The band gap can be tuned with the size of this material. Suppose cadmium sulfide 1 nanometer, 2 nanometer, 3 nanometer, 4 nanometer give the different band gap. So we can tune band gap from 3.4 electron to 1.3 electron with size in the glasses. These are this kind of glasses. There is no crystal. This is CDS crystal inside 2.5 nanometer. This may be 5 nanometer, this may be 7 nanometer. So you can see that there is a change in the band gap. Here you can see absorption. You can see the UV region. This initially it is a 300 nanometer. When you have a growth of these particles, then we can see that there is an absorption in the visible region. These are the nanocomposite. See, with color you can see there is a change in color with the size of the cadmium sulfide in the glasses. Think here, initially it is a very low concentration of low size. It's very if there is no crystal in the glass, the absorption is 300 nanometer. As soon as you grow crystals in the glass, like CDCC glasses, CDCC crystals, you can see there is a change in the absorption is going to the in the visible region with size. This is a smaller size, little bigger size, higher size. This may be 7 nanometer, this may be 2 nanometer, 3 nanometer, 4 nanometer, and 7 nanometer. So as it increases, the absorption is going to the visible region. Recently, we developed silver phosphate in the glasses, nanoparticles, and it is a replacement for cadmium sulfide. You can see the growth with Ag3PO4 in the glasses. We get different. You see in the glass, we can. This is a transmission electron microscope. You can clearly see the all kind of nanoparticles inside the glass. If you cut the glass, everywhere you will find the same uniformity in the glasses. So that is the beauty of this glass, and we use for hydrogen production. Good activity we observe. Then we started using some low temperature glasses like germanium glasses, 900 degrees centigrade. In that glass we use cadmium sulfide grown in the glasses, and band gap we can tune in the visible region, and found is a huge amount of hydrogen produced with these glasses. This is a CDCC quantum dot glasses in the germanium glasses. Here also we can see hydrogen evolution, huge amount of hydrogen evolution we observed with lower size. Then bismuth nanoparticle we developed in the glasses, and we found that bismuth is giving a very high photocatalytic, high hydrogen evolution. 11,542 micromoles means almost 2 liters per hour hydrogen evolution. Using the very smaller particles, 1 to 2 nanoparticles. If in the glass, they give good amount of hydrogen. So we publish in Green Chemistry, Royal Society journal, very renowned journal. Maybe now the impact factor is 10, but good hydrogen we have. Now we are thinking how to commercialize it for the water splitting and S2S splitting. This again bismuth quantum dots, how this size you can see very uniformly distributed quantum dots in the glasses. This is the Ag3PO4, which we have shown the structure, also shows good photocatalytic activity. And this is the reactor. This is the reactor we have on the our terrace of the lab, and this is around the capacity of this around almost 10 liters capacity, but we produce 2 liters per hour hydrogen through this reactor system. This natural sunlight we are using, and this is the catalyst inside, glass catalyst we used. So this is only the way to produce cheaper hydrogen, and we are in the process of how we can make cheaper hydrogen with this process, with a good and stable catalyst, and many students are working on this process. Hydrogen storage is also important because suppose you want to run the scooter on the hydrogen, then you can store hydrogen in the solid, very porous solid. So 5.6 kg usable is to in the 78% in the solid. If you can use it, then you can run the vehicle through the hydrogen. So many people have tried many materials. Here I have given the chart here, but now we have come up to 7 or 8% hydrogen in the. We need to go to 8 to 10%. Then I think we'll be able to do some applications. In cement, we are working on the SiO2 microspheres, and these microspheres have the channels like. And the hydrogen is stored in this kind of channels to increase the efficiency. Then we also started working in MOFs, metal oxide frameworks. These metal oxide frameworks are very porous, and there is a possibility that we can. So we started working with IOCL, this project. Now this year we are going to have some results with this framework. This is silica matrix. We can say I told you that in silica these are the channels, and we can have some kind of we can produce the material in such a way that we can have this kind of channels. This glass. Here they say I have completed hydrogen and hydrogen storage. And I think for this workshop, this is the very important. We need hydrogen at cheaper rate and how to store the hydrogen for the if you want to use it in proper automobile application. So people are also working on hydrogen storage materials. So hydrogen storage efficiency also has to be increased for the many applications. So this glass composite, this is the other application, spin-off application. I told you that glass can be worked instead of lead. We use the bismuth nanoparticles of only 0.5% nanoparticles in it, and it shows 100% X-rays absorption. So this is we made a US patent out of it. When we have bismuth sulfide quantum dots in the glasses, these glasses shows magneto-optical properties. So instead of garnet, we can use these glasses in the magneto-optical applications. So these are the spin-off applications we found in photonics. Quantum dots can be used for water purification. Quantum glass container, we can have water distillation evaporator here. We can have the quantum dots of glass inside the glass, which covers from UV light to IR region, which absorb the sunlight and evaporate this water, and we can condense it. This water purification can be done. We have a Royal Society project. We are working on that now. We are coming out some models, water purification models. Recently, we developed masks for COVID-19 last month. This is a nanoparticle coated masks. Now we are going to have this one with some of the industries for the people. So it shows antiviral as well antiviral or antibacterial, both. So we thought that let us use this kind of things in the from the so we are looking for the certificate from ICMR now for this, for large production with the help of, anyway, cement cannot produce in large scale, so cement can give up to prototype and hand over. We develop polymer swaps. which is for the indication of for the it is the part of COVID-19 kit, where the we can now we are importing it. So this kind of design we have made, and now we are going to have in huge quantities. We are transferring these technologies from industry. So now we'll have the production capacity of 1 to 2 lakhs per day pieces of these polymer swabs. So you might have heard the news that cement has developed this technology, and now we are transferred to the industry. So time is less, so I would like to conclude. This is my conclusion. So there are many things we can do, and hope that's why this cartoon I showed you, that the R&D, a lot of scope is there in materials for different applications. Even you can see in Cummins, we utilize the expertise in different directions. This is our team working in so many other projects. We have almost 27 PhD students and almost 29 project staffs and 32 scientists working on different projects. We have international collaborations, international projects. We have tie-up with ISRO, DS, BRC, and BL. So many other projects, and hope my lecture is useful to all the students, and I'm very happy to answer questions of queries of this on this hydrogen as well as other whatever maybe I have explained. Thank you very much, sir.